Okay. So good morning. So are there specific are there questions, exercises you want to study? Otherwise, we go on with this review of the course and applications. So, okay, today we do this, okay, the three principles. Okay, so the zero principle is the Baire theorem. Then the uniform boundedness, or open mapping, let's say open mapping.
Uniform boundedness and Hand-Banach.
Yes. Yes, and just Hand-Banach we did last time, so the third one I just write closed graph.
I think closed graph and open mapping is...
Everybody uses the Hand-Banach, but since we did it yesterday and I need the three, which actually are four, I just list as closed graph. Okay. So you should know this thing by heart. I mean, the proof maybe for the written exam are not so important, even if they are, but they are deep. They are not that trivial, but you have to, these are very important. They are applied every time. So let's see some exercises. Okay, some easy one. So assume that Tn converge to T pointways, and Tn and T are linear functional on Banach spaces. So pointways means that for all x, Tnx converge to Tx. Okay, just to review this stuff, okay, there are various topologies you can put on the space of linear function, linear bounded functional. So you can require, for example, that they converge uniformly. So just here, so you have
this one strong convergence.
Pardon?
This one strong convergence. Pointwise convergence.
It's called strong. Or okay, yes, it's called strong. I prefer pointwise but it's strong. They call it strong. So, for example, this goes to 0, which is the uniform. Then we have this one, pointwise. Then you can also require the convergence in the weak sense, no? So Tnx converge weakly to Tx in the weak topology. Okay, so there are several possibilities. So the important stuff is that in any case, if you go to and check these topologies, as we are doing now, they live inside the uniform bounded space. So they are different, clearly, but the sequences, they are okay, whatever they need to be. So here, indeed, we have to prove that then if xn converges to x strongly, so in norm, let's say in norm, we have that Tn xn converge to Tx. So any idea here?
Using triangle inequality.
Yeah, but so we need to use one of these principles.
Ah.
You need minus something and plus something.
Pardon?
Minus something and plus something, then you break it down.
Okay, so you
using
want to
triangle
write
inequality.
Sorry, this one less or equal than what you want me to write? What do you want me to write now?
What? Then we uniform boundedness we use here tn minus txn plus txn.
Txn minus x, tn minus tx. And then?
Okay, then just one. Okay, if we use uniform boundedness, then the norms of Tn is bounded.
Yes, by uniform boundedness, so this is less or equal than norm of
N
Tn,
maybe.
xn minus x. Okay, and this guy doesn't matter, this converges to 0, no?
But strong convergence, just condition of problem, that one.
Now the thing is about the supremum of this guy, but then you apply the uniform boundedness. It says that if you have a family of operators which are pointwise bounded, then they are uniformly bounded. So in this case, clearly the convergence implies that they are pointwise bounded. So Tn of x, let's say that the sup, so let's say for all x there exists C of x such that the norm of Tn of x sup is less or equal than Cx. Because there is a limit. So the uniform bounded tells you that hence, so the norm of T, so the sup that existed, say some m, the sup of the norm of Tn is less or equal than m. Now we conclude, because this guy is less or equal than, well, m norm xn minus x plus O1. Okay, so this is a classical exercise, classical questions that you can face. Let's see if there is another similar one. Complicated. Oh, yes. Same thing. Well, with some variation. Let A from E times F into, let's say, it doesn't matter, R, be linear, and, okay, I will write for shortness that is separately continuous, so continuous. So what does it mean? It means that, so if I fix x, or if I fix y, okay, is a linear functional in the dual of E star, and if I fix x,
it's continuous, it's bounded by U-B, but Banach goes. Okay.
Then, okay, then the result is that then A, then exists a constant m, A, x, y, less or equal than m, norm of y.
We fix y, and then each of AX, y is just some mapping, bounded mapping. Then we apply Banach-Stengauss for this family. Family is just y is Rams over phi.
So if you think at this operator, this is a bounded operator, and so for any y, the norm of or whatever okay, I think I don't know.
Y is the parameter, and
So,
X
yes,
is...
yeah, indeed. It's the same exercise as that one. So you apply the uniform boundedness to the mapping A of X, Y, and then they're uniformly bounded by a constant M, which depends on, which does not depend on Y, and then you conclude. So let's say, I think I can leave it to you, no? This is, again, uniform boundedness. I don't know, you want me to go on, or? So you apply to the point that X maps to, let's say, the function, the linear functional Fy X, which is equal to A xy. Now you take y, for example, in normal y less than 1. So you have a sequence of parameters, and because of the continuity of the second one, you have that this guy is bounded, for pointwise bounded for any x. Because we know that for all x, so the supremum of the modulus of A xy for y less or equal than 1. So being this guy uniformly bounded is less or equal than the constant which depends on x as before. Okay? So we apply uniform. So this tells you that you have a family of linear functionals parameterized by y, which are pointwise bounded. So the uniform bounded principle apply again. So there exists this constant m such that the supremum. Oh, sorry. So this is, and actually I can say this is less or equal norm of x. So I'm fine. A x y, and so let's say norm of x less or equal than 1, y less or equal than 1, or let's say the norm, whatever. This guy is less or equal than this constant m, because they're uniform bounded. Okay, so then you just take a 1 on the other side, and then that's it. So again, this is the way, I mean, these are very classical exercises. Oh, let's see this guy here. So interesting. Okay, let's change a little bit. Let t is a linear function from E to the dual such that, is monotone. Which means that t x x is greater or equal than 0. Then t is bounded. Okay, so here I have to bounded, which means I forgot. Is a mapping. Otherwise, in the hypothesis, is from E to E star. Otherwise, it was in the assumption. So I don't know. I know it just is linear. Then it is bounded. Okay, if you go back there, so what works for this thing here is the closed graph. No? Okay, so we prove that T has closed graph. Okay, so what does it mean? It means that if xn converges to x and txn converges to y, then tx equal to y. This is the definition of closed graph. Okay, so we need an inequality, but we have linearity. So the idea is always to take small perturbations in order to, when you have the linearity, well, then you change sign of the perturbation and you get an equality, and the equality will tell you this. So take So take, for example, so we have xn converges to x, so Zn xn plus 2 to the minus n, let's say, w. So we have again that Zn clearly converge to x again. And now we use the hypothesis. So T, by assumption of Zn, okay, I need Zn minus Tx. Zn minus x is greater or equal than 0. So let me write now what's happened here. So now we have that t, this is txn minus tx, okay, txn minus tx, sorry, this I have to keep, plus 2 to the minus n t, sorry, I have, let me see, probably is not the best one. Sorry, and this one, yeah, okay, it's okay. And now it is xn minus x plus 2 to the minus nw.
First, in the first term, you drop W.
Okay. Okay,
First,
so this guy,
minus
so let me write. So let's say we have this guy, I forgot to have here w. So now we write like txn minus tx. I need the points which are interesting. So xn minus x. Sorry, I think I need that is I keep epsilon. Let me keep epsilon here, because otherwise I have some problem, epsilon. So this is the first, then I have plus epsilon, and I get tw xn minus x plus epsilon. I have txn minus tx w plus there exists epsilon squared and whatever is left, that is tw w. So we pass to the limit. So this guy converges to y minus dx. But actually this guy converges to 0, so I don't say anything. So the limit is epsilon t w. Okay, and this guy goes to 0 again, sorry. So what is left is epsilon. This is y minus dx, because txn converges to y, this is my assumption, w plus epsilon squared tw greater or equal than 0. So this holds for all epsilon. So you must have then y minus txw is greater or equal than 0 for all w. Because if it is negative and epsilon is sufficiently small, this is bounded because it's a point, and so I get that the thing would be negative. So the only thing is that essentially it's like the first derivative with respect to w, or you divide by w, let w equal to 0. Okay, but then if this holds for all w, the only possibility is that y is equal to tx. No? Because take w minus w, and then if it is non-zero, there exists a vector by definition, which makes no sense. Okay.
Excuse me, Professor.
Yeah.
I have a question. He said to show that C has a closed graph, we have to show that if Xn converges to X.
Xn converges to X.
And this converges to Y, then Tx is equal to y. I don't understand why that is sufficient to show that it has a closed graph.
Sorry, I have difficulty understanding the question. I'm sorry, because the audio is not particularly good. So can you repeat or just write in the chat, maybe?
Okay.
Is easier.
I will write in the chat.
Okay, thanks. So it means the following. So you take, so the question is, what is a closed graph? So the graph of T is, by definition, is the set of X and Y, which belongs to the E times F, if T maps E to F, such that Y is equal to Tx. Okay? So in the product space is the set of couples such that Y is equal to Tx. And now you want to say that the graph is closed. So what this means that the point is closed? Now we are in metric spaces. So the graph, the graph of T is closed if you take a sequence in the graph, xn, yn, which belongs to the graph, and they converge strongly. So they converge in norm, in the product norm. They converge to xy. Then the limit belongs to the graph. This is the definition of closure, no? A set of closure, if you take a sequence converged with metric spaces, at least a sequence which converges to something, the limit is in the set. So now we have just to express the fact that they are in the graph. So now xn, yn is in graph. So equivalent to say that xn and txn. Okay?
Yes.
So the convergence, now the convergence means that xn converge to x in E, in the norm of E, and yn converge, the product norm is yn converge, no? So which means txn converge to y in F. And the closure is that being in the graph, y should be equal to T of x if xy is in the graph. So it's the statement over here. Okay?
Yes, thank you.
Welcome. Okay, then there are some another of the same structure, and we are not going to solve it because it's completely similar. Well, it's not even completely similar. It's even easier. So T from E to E star such that Txy is equal to Tyx. Then T is bounded. This is even easier. I mean, you don't need to do basically anything. We are not going to consider it. Change a little bit. I have to say to the technical support, there is some smell of something burning here.
Okay, we'll send a technician.
I don't know, maybe it's just some feeling. Now I don't feel it anymore.
Okay.
I don't know, it's slightly...
I'm going to send the maintenance guy.
Okay. I don't know if it's... Okay, let's do something about the orthogonality and duality, whatever. So let's consider, for example, the operator T. Okay, just to not forget, there are several questions here. So T is a linear operator from L1 and L1 defined by TU. Okay, okay, U is a sequence, and this is the sequence UN over N. Okay. So, first question is, what is the kernel? Okay, we answered the question. So, what is the kernel?
It's what? Injective.
Is injective, because, okay, so you have to say the kernel are all the U such that TU equal to 0, and TU equal to 0 means UN over N equal to 0 for all N, so UN equal to 0 for all N, which is U equal to 0. Okay, so now what is the orthogonal of the kernel? You remember we had this orthogonality relation in, when we were studying the Hilbert spaces. No? So what is the orthogonal?
Full L infinity. Full what?
So
dual space who L infinity.
Yes, first of all, it's in the dual. So the kernel of T orthogonal is contained, well, okay, here this is not T star, so I consider as a primal, because you know that in L1, I have the, was not clear, I mean, if I give you a subspace, what is the orthogonal, no? Because the orthogonal can be in C0. So let's compute in two cases. So when it's considered as a subset of L infinity, what is the orthogonal?
Full space L infinity.
The whole space, because
Equal.
the orthogonal by definition are the vectors V in OF in L infinity such that the duality is 0, but now for all U which is in the primal space, which is the kernel of T. But now kernel of T is only the vector 0, so 0 times any F is 0. So this is equal to L infinity. And on the other hand, if I consider instead this is a dual of C0, so I can consider also the kernel of T as a subspace of C0, because I know that the dual of C0 is L1. So in this case, it's clear that I want to use more or less L infinity, but it's not that clear. So in this case, what is?
L1?
No, so in this case, it's again C0, no? Because same computation. the kernel of T orthogonal, if I consider L1 as the dual space, is exactly C0. Okay?
Yes. Yes, okay.
So let me, maybe you're confused, but let me say what is, so you have E and E star, and I have M subset of E, linear subspace, or even subset. M orthogonal are all the F such that F U equal to 0, U in M. And if I have, let's say, M star, E star, then M star orthogonal is all the U such that F U, so this is in E, is equal to 0 for all F in M star. So just notice, but that here was not clear because it's not said in the statement. If from this definition you can consider L1 as the dual of C0 or L1 as the pre-dual of L infinity. Okay, so the answer in any case is easy. So now we have to compute the adjoint. The star being an adjoint is a map from the dual, okay, into what?
Dual.
The dual, because of the space is the dual of the end space into the dual of the first space. So what is the form of T star? So you have to remember always that the basic thing for the adjoint is T star F, F, T, U. Okay? So now you compute and you get it. So T star.
Same. Form same. With
Pardon?
this. T star F equals to Fn over N, that sequence.
Yes, because this is the sum, by definition of dual product, Un over N, so which I write like the sum Un. Okay, so the T star acts on F is the sequence Fn over N. And then if I okay, which I can deduce is applying the previous exercise that it's already bounded if I don't have the explicit formula. So now we compute the range of T star.
Gilbert brick 1 over N, product of segment.
Okay. Is what? I have to range of T star are all the sequences such that
NGN bounded.
N, Gn, yes, is bounded, because from this guy is bounded. So the sup is less than some M. So there exists M for some M. Okay. So what is the closure of this space? So what is the closure? So let's see. I have a sequence, Gn, the range, which converges to another sequence, G. Then
Is it CNR, Professor? Or is it smaller than that?
okay, so I think I did not manage this thing. So I did not conclude. I want to just say that is not the complete. So now I need to think a little bit. So n Gn some doubt here. Sorry. Okay. Okay, so I say that the closure, so the closure is C0. Because this is, so if, let's say, because I observe the following, that the finite sequences are contained in C0, are dense in C0, okay? And finite sequences, that is C compact, is contained in a range of T star. Clearly, this holds whenever the sequence is finite. On the other hand, the range of T star is contained in C0 because the limit of any image goes to 0. So if I conclude, I get that the closure of this guy is equal to C0. Now let's go back here. And indeed now the proof is correct. Because if you remember that the two things, so let me write now the theory about these things. So the theory is that the range, so the kernel of T orthogonal which is L infinity here, contains the range of T star closed, which is C0. And in our case, is different. While, because of the Hahn-Banach theorem, we have the opposite inclusion is equal. So we know that the kernel of T star orthogonal is equal to the range of T closed. Indeed, the range of T contains, again, C0, contains the finite sequences, and finite sequences are dense in L1 with respect to the L1 topology. So what we have shown here is an example where, the results that we had, that is estimates, and then we have the other one, which is the range of T orthogonal is the kernel of T star, and the range of T star is the kernel of T. So we have this, if you remember, we did these computations, and then since we cannot apply Hahn-Banach theorem, we didn't get the result is. Well, in reflexive spaces, we could get. And so the exercise is an example where the inclusion is really strict. And okay, if you look at the exercise, just to think, so the trick is really that L1 can be thought as the dual of C0. So I am applying now the second one, and I get C0. So in this case, the kernel of T star is 0, the orthogonal is C0, and this is C0. Or if I think instead in the B dual, which is L infinity now, I get the strict inequality. This is a nice exercise, I like it. Okay, are there questions? Otherwise, we change subject.
But Professor, C0 is bigger than L1, as I just said.
Yes, is bigger than L1, yes.
But
I use that the finite sequences are dense. So the image of this guy contains the finite sequences for whatever P you put here. So in order to prove, let's say, this guy.
yes, but we go out from our space because T from L1 to L1. So
Yeah, you're right. Sorry. Here I want to apply this guy when T is this functional applied to C0.
Domain is different. Domain is
Yeah,
C0.
it's different. It's a different T. So I call the previous T, I call T star here, just to keep the formulas that we have in the textbook. Because otherwise I should give another, so I should give something, let's say this is T, and then I say this is the range of T star to the -1, T minus star, the previous one. Okay? So it goes like, which is T considered on C0, not on L1. Because T is always the same. So T star is T considered in L infinity, T is T considered in L1, and then we'll say T minus star is T considered in C0. Something like this. T minus star of U, this is from C0 into, let's say, C0, which from UN, you give UN over N. T L1 is always the same. L1, and the map is the same, and T star L infinity into L infinity. So the second formula, I apply between these two. So the kernel of T orthogonal is the range of T star here, but the range is dense in C0, so it is this C0. But in the other thing, well, you cannot change the argument because the norm of C0 is the same as the norm in L infinity. And so you obtain that the range is again C0 as here, but the orthogonal in L infinity you have more space. And so you have the inequality here. It's a little bit subtle, but is an example. It is to see that it is sharp. We are not inventing something. Okay, something on the adjoint again. No, I think it's enough. Let's go to the other subject. The other subject is weak topologies, and we have some fun here. Here there are a lot of results. So I will try just to say which one you use, or I use. Maybe there are others. So weak topologies. So now we have first the weak and the weak star topology, the two definitions. So in the book they're called sigma E star and sigma E star on E. So I don't remember which one, if this one is the weak, one is the weak, and the other is the weak star. Okay, and now we start with the theorem. Okay, these topologies are weaker than whatever, and so the first thing is that convex closed sets are okay in weak, which means that if it is closed and convex in the weak, on the strong, it doesn't matter. But clearly in the weak, if it's closed in the strong, vice versa, is because of the Hahn-Banach. So first thing, we have a very good characterization, which is not true in the weak star. But in the weak star has other properties. So the other property is that the unit ball, so the ball, let's say of radius, doesn't matter, R, contained in E star is weakly star compact. Okay. So in order to merge the two stuff, we have the reflexive spaces. Where essentially it means that weak is equal to weak star. Let me write this way, no? Because if you embed in the B-dual, essentially, so what you get is that closed convex, closed convex bounded sets are weakly compact. And now, weakly compact, and so what about subsequences? Because the topologies cannot be metrized. But you know that if E star is separable, or whatever, then the weak topology restricted on let's say the unit ball or any bounded set is metric. And so now we are okay because we can talk about sequences. Okay, and then there are other results. So for example, that if you, what is important to know is that if a space is uniformly convex, so the unit ball is uniformly convex, then it is reflexive. But okay, these are the things to be recalled. What is important is, for example, is that another property which sometimes is asked. Well, if E star separable, then E is separable. So the weak topology, well, it's separable. And the other thing is that no matter of the separability, if E is reflexive, okay, or maybe let's say if reflexive xn is contained in E bounded, then exists a subsequence weakly converging to something. Well, there are so many results, let me say. These are some, because there are so many. For example, the other one is if xn weakly converge, then xn is bounded because of the uniform bounded principle, so whatever. So let me stop here by just saying that this page is more, well, with corollaries like this one is something you need to know. Okay, so we have now some exercises. Let's see what I can. Okay, let's start with the fact that, so I want to make use of the compactness. This one. So compactness means existence. So wait. M a linear subspace. Subspace, let's say it's enough. And F0 belonging to the dual, then there exists G0 in the orthogonal such that the distance F0 to the orthogonal is equal to the norm G0 minus F0. Okay.
My idea is that for this question, norm is lower semi-continuous in weak star topology, and any lower semi-continuous function attains its infimum in compact set.
Okay. Yes. Yes, the thing is correct, but let's see. Okay, I do it by hand, but okay, the distance is lower semi-continuous, and M, what is the compact set? So it says that you consider G
take minimizer
M
and
orthogonal, which is closed into G minus F0. So
we choose some
so
bounded
this function is, by definition, is because of the representation of the norm. Okay, which is correct, but what is the compact set now? But then I will do by hand.
First, let's take any minimizer sequence.
So Gn such that the norm of Gn minus F0 converges to the distance of F0 M orthogonal.
Gn is bounded, we can show it's bounded, and we can choose ball that it contains all Gn.
Bounded, so Gn, norm of Gn less or equal than some, let's say, M. Well, M is some constant C.
And we take some ball contains all Gn's, closed ball, strong topology. And this closed in strong topology ball is weakly compact.
So the ball of 0, C in E star, we have from that one, which is weak star compact.
Yes, and there is G0 in this set, in this ball.
Should be in M orthogonal.
intersection.
M orthogonal, the observation is now, is weakly closed. Okay, by definition. So, yes, because M orthogonal is the intersection over X belonging to M, or of F, such that F X equal to 0, and this is by definition is a closed hyperplane, weakly star closed hyperplane. Okay, so you take now the map, so you have the compact set.
Intersection of two.
Okay, now?
This one is, then we consider norm. Norm is lower semi-continuous function on this set.
Yes, okay, well, yes.
Then there is some G0 and
Why this is going to weakly converge, weak star converge?
G0 is infimum in this set.
But yes, okay, so the G is a sequence in a compact set, but I'm not saying that it is, E is separable. So, if in the exercise you solve it and then you say, let's take E separable, and then you do by sequences, okay, for me it's fine. But you have to state it. Otherwise, if it's not separable, so at least you know that there could be some problem. So the thing is more or less okay, but we need to use just this. So if Gn, so take a compact set, let's say K epsilon, which is equal to the ball of radius, okay, which is equal to the G in M orthogonal such that G minus F0 is less than the infimum, less or equal, of, let's say, less or equal than the distance plus epsilon. Okay. And now the previous, so this guy is the intersection, by definition is M orthogonal intersection, the ball, centered in F0 of radius, the distance, plus epsilon. And then we know that this is compact. And now the intersection over epsilon of K epsilon is non-empty, because the finite intersection is non-empty, so the intersection is non-empty. And so there exists a G belonging G0 to the intersection, and by definition, the intersection is only the point such that D0 is equal to the distance. Okay? So yes, the proof was more or less correct, but there is this, I don't know, is your feeling, this stupid subtle thing or not stupid subtle thing, that if you use sequences, you have to be careful about the topology, okay?
But Professor, in our previous reasoning, we can show that G0 is the infimum. Just we use.
But where is G0? And why Gn is weakly star converging to G0? I'm asking this guy.
No, I don't claim this.
Okay. And then what is G0?
G0 is infimum because norm is lower semi-continuous function. only weak star topology, and our set is compact.
So the proof is here.
No, in the previous reasoning.
The previous reason you said you take Gn which converges.
Yes.
Yes, and then you have a point whose limit. So I'm saying why the limit is non-zero.
What limit?
Because you observe that the level set is the intersection of level sets. So you need to use this guy here. Otherwise, why we need the Gn?
Okay, then can I write you by email just my?
Yes, yes. I think at the end you use this observation. So if you say because it is a lower semi-continuous function in a compact set, then, okay, the proof is this guy here. Lower semi-continuous functions in compact sets have a minimum, simply because you take the intersection of all level sets. And the intersection of low in the level set, like I'm going here with the epsilon, you get something. But you cannot use the sequences. This is so easy. Let's see. Okay, let's do something on measures, just to have fun. Okay, so let's say so E reflexive K contained in E is bounded, okay, closed, convex. So immediately it should sound to your brain that we are going to have some weakly compact set. So consider the set of measure over K, which is like the dual of the continuous functions on K. So, and this is the function of K with a weak topology. Okay, it's a compact set, so there are continuous functions with the topology, and I take in the measure. Show that for every measure, there exists a unique zero in K such that fx0 is equal to the integral fx mi dx. Okay, where f is considered as a continuous function over the over K, no? So roughly speaking, what I'm saying is that, so let me write roughly speaking, x0 is the integral of x, is the barycenter of the measure. Okay, so let's do this.
What center?
Hmm?
What center?
barycenter, one.
Okay.
Okay, so essentially it's like the center of mass. Center of mass. Okay, how to do that? So I just observed that f maps to the integral is a weakly continuous function. Sorry, so it's a linear continuous functional on E star. Because if f converges to, so let's call this guy, well, whatever, if f converges in norm, this object clearly converges pointwise, actually uniformly, and then, okay, you can pass to the limit. So the convergence in norm of f is equal to the convergence, is the equivalent, actually is equal to the convergence in CK. But more or less. Because, okay, so if K is not empty interior, otherwise it's slightly different. So this is a linear continuous function on f, so I know by the, so this is a linear function by reflexivity that exists an x0 such that f x0 is equal to the integral fx mid x, and actually it's unique, no? Because this guy is a linear continuous function, and by definition of reflexivity, all the linear continuous functions are represented like as a vector of the pre-dual space x, E. So this is some x0. So now the thing is that y should belong to k. So if x0, okay, I make just the drawing, does not belong to k, so let's say this is my k, this is my x0, so what I do?
Separate, for example.
Pardon?
Separate, just using.
I separate, I strictly separate.
Yes.
So I have some f, so that here f on k is less than alpha. I forgot to say that the mass of me is bounded by 1. So it is a probability. Otherwise, it doesn't work. So it's still a representation, but it's not. And f of x0 is larger than alpha. And now the integral of f x me is less than alpha. So it's a contradiction, cannot be represented by an x0, which is not in the set. Oh, so let's have some fun in this other exercise. So consider okay, what is called the Schauder base for LP is 1 in the end position, 0, and so on. These are vectors in, okay, whatever it is, L1, L infinity, any P. So, first point. En weakly converges to 0 for P 1, okay, let's say P1 and infinity, or En weakly star converges to 0 in L infinity. But this is just a routine. Okay? I don't know, you want me to do that or you know?
No, no, we know.
You know, but I don't know the other.
Please do it. We would like you to do it.
Do you want to see? Okay, so let's start. Well, here, what is the dual of these sets? So for P1 infinity, the dual is, as in the whole measure space, is LP prime, 1 over P prime plus 1 over P equal to 1. So and this gives that P prime 1 infinity. And what is the dual in this case? The pre-dual, so L infinity pre-dual is L1. So at the end, I have to prove so I take F times En, where F is either from 1 to infinity or P prime equal to 1 here. So it's the sum Fn En that this goes to 0, where F belongs to L P prime and P prime is 1 infinity. Okay? So now what I do, well, since it is integrable, okay, because this means that the sum over Fn to the P prime is less than infinity, so I can just take, okay, so this implies there exists, for all epsilon, there exists an index, let's say capital N, such that Fn less than m for all n greater than, sorry, less than epsilon for greater than n. Because the sum should converge, and so definitely the elements should be small.
0.
Okay, so and now we write that sum. So this is the sum up to n. So I can put like Fn En plus what is left. Now this guy is less or equal than, okay, this guy if n, sorry, here I did a mistake because at the En I used the index twice. So let me, this nk, let's put the k above. Otherwise, I'm confusing so I have two indexes here. So now if n is larger than capital N, you see that it is 0. So if if n is larger than capital N, then this guy is 0. So what is left is the rest. And the rest is the L1 norm of this guy times the L infinity, which is epsilon. So it's less than epsilon. Which means that the limit of F(En) is equal to 0 for all F. Okay, so this is the easy part. Now En is not converging to 0. Okay, this is the but, let me just write here, but En does not converge to 0 in any norm you want, because the norm of En, okay, in any space you prefer, is equal to 1. So now we want to show that there exists a sequence. So now we want to say what happened when I consider En is in L infinity. Sorry, as in the dual of L infinity. Okay. This is a converging subsequence. So we want to exploit the fact, the non-trivial fact that the compactness, if we go back here, the compactness here is a topological compactness. It has nothing to do with sequences. That's why the assumptions on reflexivity plays a role. Okay, what is the answer? So I'm saying that, so suppose ENK converges weakly to something. And what is the limit?
Zero must be.
That
Because
should be 0. But it doesn't matter here. Let's say it converges equal to 0. Okay, which means a weak star, which means that for any G in an infinity, the scalar product, which is what?
sum, yes. Scalar.
Scalar product is sum Gn En, which is, sorry, Gk Ek, which is equal to Gn. So let's say GL. So it's G and K, the K and index, it should converge to 0. And then? So you deduce, clearly this cannot be, no? Because take G is the characteristic function of the family Nk. Then you get a contradiction, no?
Professor, what is the characteristic function of MK?
Pardon?
What is the character?
G and K 1.
Means that G is the sequence which is 0 if L is different, does not belong to the subsequence of indexes, or 1 if L belongs to the subsequence of indexes. And okay, you can even play with plus or minus in order to get that it is not converged, no? For example, if so I alternate plus or minus, whatever, then you get that the limit does not exist, which is even better because a priori you don't know if the limit is 0 here. But the question is meaningless because it does not converge. So the exercise shows that, that the topology, the topology is non-trivial. Okay, let's do another exercise just to end this part. Okay, let's show that the property that I stated here, so that you have a sequence which converges weakly to 0 with norm 1 is general. Will be the last. So I stated the exercise with an hypothesis lacking. Well, if you have the book, clearly you look at the book, but then you have to say why it's lacking. So, E Banach, and then something is missing. There exists xn, norm xn equal to 1, and xn is weakly converging to 0. So what is missing here?
Reflexivity.
Yes. And in fact, a good exercise is the following that you want to do is that in E equal to L1, and xn weakly start converge to x, then xn strongly converge to x. Because the dual space L infinity, so more or less you repeat this approach. And with this approach, essentially, you choose the test function in L infinity such that the weak convergence becomes the strong convergence. But okay, now we do the exercise. So how to do that?
Let's take constant sequence.
I need the norm to be constant. Yes, so what I do? Okay, if you want to have something easier, then you can take Hilbert. Then we can manage. So for Hilbert is easy, no? What you do for Hilbert?
What Hilbert question? If sequence weakly converges, it's strong converges?
Hilbert, yes, there exists a sequence of unit vector which weakly converges to 0.
Gilbert just reflexive, so we can deduce.
Yes, but I mean, for the proof, how to do the proof. I mean, if you don't have any idea how to do that, I suggest you to look at the Hilbert case, and then you generalize. Okay, so let's see for the Hilbert. For the Hilbert, you take an orthonormal base.
But yeah. Hilbert plus separable.
You don't need it. Because then we are going to use the following thing, that if you take a sequence and it's bounded, there exists a sequence which converges simply because you restrict to the space generated by these vectors, which is separable, and then you know that if a closed subset of a separable space is separable. So this was one of the theorems. No, En then weakly converges to 0. Simply because, well, having F is the sum of F En, and then you have the sum of F En. Well, okay, if it's separable, otherwise it's just one piece. The projection over the span of En, and then you have that this guy is equal to the norm of the projection of F squared. So the sum should converge to 0 for any F, which means exactly that the limit is 0. So how to do for the Banach? So for the Banach, we can assume that E is separable, and also E star is separable, clearly, and finite dimensional. Infinite dimensional. Okay, by just taking, okay, otherwise then it is finite dimensional. So there exists a closed subspace which is separable, and then you just work in that closed subspace. So now what you do?
Your question is constructing concretely
Yes.
some sequence.
Construct a sequence. So it's like this one.
Maybe we can use Riesleman just.
Which
We
theorem?
take what some
Okay.
linear
you have to
independent
prove
vectors.
that f.
Huh?
You have to prove that for all f in E star, or let's say in a unit ball, doesn't matter, f of xn tends to 0. Okay, so now since E star is separable, I just suggest it. So if you remember, this is f scalar product with something, and I do the same. So let fn be dense in the unit ball, and take, okay, I just sketch it, let me see if you understand, because so let's say x0, such that, okay, this is normal, okay, dense in the sphere, so just for easiness, equal to 1, just not to make too many things. x0 said that norm of x0 equal to 1, and f0 x0 is equal to 1. And this exists because it is, well, it is reflexive. No, because I have the supremum, but being reflexive, I can obtain that there exists a maximum. Okay, now what I do? Take x1 belonging to what? So now it's the distance of x0 from, let's say, the space generated by x0, x1 is equal to 1. And I take the norm. So being, again, reflexive, I can take this guy equal to 1. So essentially is the one which stays, that is not unique, like in the Hilbert space or in the convex space, but there exists this point because of reflexivity. And moreover, they are a lot, and then I can assume that f1, x1, okay, another one, well, the first in the sequence which is greater than 0. Doesn't matter what it is. It is less than 1, but greater than 0. So in this way, I have a sorry, x1, which is sorry, it's a mistake. Is in the kernel of f. Sorry, this is a mistake. Is x1. I take in the kernel of f0, norm of x1 equal to 1, and then I want to ask that f1, let's say, well, that doesn't matter. Then sorry, I'm just confusing the stuff. It's just that I definitely, so the idea is that definitely is 0 for any, and so let's say x0 belongs to the kernel of f0, and then I have xi belongs to the kernel of the intersection of the kernel. Okay, this is much easier. Norm of x0 equal to 1, and this belongs to the intersection of, sorry.
From 1 to I.
Yes, I need minus the kernel of f1. And then I take x1 belongs to the kernel, because I need to be, wait, I mean, first, perhaps I don't need it. Let me just think. So this is x1, x0 equal to 1. So I take now x1 is in the kernel of f0 intersection the kernel of F1 and norm of X1 equal to 1. And so at the end I have Xi belongs to the intersection up to I of the kernel of Fj, and the norm of Xi is equal to 1. Okay. Yes, that's enough. So what happened? This is a sequence which has a norm 1. And so let's see what happened. And Fn, for any n,
Constant.
is definitely constant. From and for Fn, applied to the sequence Xm is equal to 0 whenever m is larger or equal than n by construction. Okay, now for generic F, I just write F minus, okay, there exists some alpha Fn. This is less than epsilon. And then you do the same. So now you write Fxm. So Fxm is less or equal than epsilon, because this guy applied to Xm is 0. Okay, it's just, sorry, I was confused earlier, but it is the orthogonality relation, no? So every time when you, in the Hilbert space, you subtract the one component, and then the other ones are orthogonal. And in my opinion, the orthogonal means that they are in the 0 kernel. Okay? So I think we can conclude today. I'm sorry, I had a lot of work this week, so I could not manage too much. And see you on Monday for the last one. I think that then the sample will be ready by the weekend. I hope so, because I have still to do some work tomorrow. Are there questions? Otherwise, we see you Monday at 11. No, I think, if I'm not wrong, it's the same time.
Thank you, Professor.
Yes, Monday at 11. Okay. So see you on Monday. And just write me for every help you want. You know what is the date of the exam?
8th.
You know?
Of March.
The 8th of March, yes. Okay, yes, they told me, I just forgot.